We've been discussing the power supply for a pneumatic control system. In this section of our program, we will discuss how that power or air supply is put to work. This is done by the control devices, the damper actuators, and control valves. These devices provide the means of controlling or regulating the media, such as air or water, that is being controlled within the heating, ventilating, or air conditioning system. Air pressure is converted to a force by utilizing a signal pressure to operate an actuator controlling a valve or damper. The valve body or damper provides the means to regulate the controlled medium. We will discuss the various damper actuators, and valve body configurations in this section of the presentation. First, let's take a look at the construction of a damper actuator. The actuator housing holds the spring and the actuator shaft, which is attached to a diaphragm cup. The diaphragm is molded in a cup shape with a sealing edge to conform with the outer edge of the actuator body. When assembled, the actuator cap is bolted to the actuator housing to form an airtight seal in the cap end. Air pressure is provided at an entry point in the actuator cup, placing air pressure on the diaphragm. This pressure transfers its force to the diaphragm cup, compressing the spring and extending the actuator shaft. Dampers are referred to as normally open or normally closed. Both of these operating conditions exist when there is no air pressure applied to the actuator connected to the damper. Here we will use a demonstrator to illustrate both normally open and normally closed damper operation. Notice the damper linkage in both cases. A normally open damper is directly linked to the actuator. So when the air signal is removed from the actuator, the internal spring retracts the shaft and the damper returns to its full open position. A normally closed damper has its linkage connected so that when the air signal is removed from the actuator, the internal spring retracts the shaft and returns the damper to its full closed position. Robert Shaw offers 4 distinct sizes of damper actuators, generally referred to and selected by stroke length. These actuators come in 2, 3, 4, and 6-inch strokes. The larger actuators have a greater diaphragm area, allowing them to handle larger dampers. The actual amount of damper area that an actuator can handle is dependent upon the spring range of the actuator, quality of the damper construction, and the rate of airflow across the damper. Another factor that must be considered in selection would be the type of application, either two-position or modulating. Detailed sizing information can be found in the individual product data sheets. Shown here is the right angle mount, one of 2 common mounting styles. This type of mounting provides a rigid mounting method for the actuator. The actuator shaft is connected to the damper by ball joints, a push rod, and a crank arm. The post mount actuator is attached to the mounting bracket with a post assembly and is free to swivel on that post. In this application, the actuator is connected directly to the crank arm rather than using linkage. Here is a 3-inch actuator, the 2473 series, with a positive positioner attached to it. A positive positioner is used to properly sequence single, or in some cases, multiple damper actuators within the control sequence. The positioner is used where the position of the damper is critical to system operation. The positioner utilizes a main air supply along with the signal input from the controller. A feedback arm and spring connect the actuator shaft to the positive positioner, linking movement to the input signal. The start point of the actuator is adjustable at the positioner. The stroke of the actuator occurs over a 5 or 10 PSIG span. depending upon the feedback spring utilized. The ability to adjust the start point of the actuator provides the ability to fine-tune the resulting damper action to fit the desired control sequence. Shown here is a 2466 series actuator applied in the field. This is the 6-inch stroke, post-mounted model, applied in a vertically mounted position and linked to a normally closed damper. Having discussed damper actuators, let's look at valves and valve actuators. There are two basic types of valves in this presentation, two-way and three-way. Two-way valves are available in two types of body construction. They are normally open, which is also referred to as air to close, and normally closed, which is also referred to as air to open. These descriptive terms refer to the position of the valve body and actuator combination when air is removed from the actuator. The first flow pattern shown is of a normally open valve. Note that the flow through the valve body is from left to right, and that the valve is open, allowing flow to pass through unaffected. This is a normally closed valve, with the valve plug shown on the seat with flow blocked. This is the valve's normal or at-rest position. Here we have a cutaway of a normally open control valve and actuator. The actuator detaches from the valve body by first removing the clamp nut as shown. This enables the actuator to be lifted off of the body. Next, unscrew the spring adjusting nut and lift off the spring seat. Then remove the valve spring. The components within the valve body assembly include the packing nut, packing, valve bonnet, stem, and plug assembly, and the valve body and seat. To replace the packing, first remove the packing nut and then the packing. By removing the bonnet from the valve body, the stem and plug assembly can be accessed, removed, and replaced. This is a normally closed valve body assembly. The spring pushes up against the spring adjusting nut, pulling the plug assembly up against the valve seat. This valve body utilizes the same actuator as the normally open valve. The packing assembly in the normally closed valve is identical to the normally open valve. Note that the valve body is of a different casting than the normally open valve. First, remove the plug on the bottom of the valve body. Then, remove the stem and plug assembly through the bottom of the valve as shown. Two-way valves and their actuators come in a variety of sizes. Shown here are a few of the valves available with their body and actuator configurations. Valve body sizes range from 1/2 to 4 inches, with actuator sizes ranging from 3.5 square inches to 80 square inches for the larger models. There are two types of three-way valves, mixing and diverting. By far the most common application is that of a mixing valve, which is intended for modulating service. A diverting valve is generally used to divert the flow either through or around a piece of equipment, such as a cooling tower. A three-way mixing valve is piped with two inlets and a single outlet, referred to as a common port. As shown here, the supply is feeding both the upstream side of the coil and the normally closed port of the valve. The normal condition is with full flow through the coil. As the process calls for a decrease in heating or cooling, the plug assembly of the valve moves down, opening the normally closed port slightly. which starts to reduce the flow through the coil. This valve has the capability of going to full flow in either direction, but generally mixes or modulates the flow. It is designed to mix the two inlet ports, modulating the flow through the coil. This cutaway of a three-way valve shows a different style of valve plug. As indicated by the previous line drawing, the plug itself is tapered towards both ends and has a metal surface, closing against a metal surface. The valve is shown in the normally closed position with full flow through the bottom of the valve and out the left side. The bottom seat is machined into the threaded assembly, which is screwed into the bottom of the valve. The stem and plug assembly are removed through the bottom of the valve after the bottom plug has been removed. This is a three-way diverting valve. In this particular application, note that the flow to the valve enters the common port and exits through either the normally open port, which bypasses the cooling tower, or through the normally closed port, which goes to the cooling tower. These valves are meant to be used only in a two-position mode of operation rather than in modulating applications. However, some mixing valves are specifically designed for both uses. Shown here is a small grouping of the many different styles of three-way valves that are available. Please note the different body configurations, piping connections, etc. Actuator sizes, again, range from 3.5 square inches to 80 square inches. Shown here are two larger style three-way valves, which are available in sizes of 1/2 inch to 6-inch pipe size. There are other items of valve nomenclature that are used in various HVAC applications. One of these is the specification of a flow characteristic for a valve. There are three principal characteristics: linear, equal percentage, and quick opening. HVAC applications will usually be of the linear or equal percentage types. To better illustrate the flow characteristics of control valves, let's take a look at them, one at a time on a graphic basis. First is a quick opening valve. Note that we are comparing the amount of stem travel with the percentage of full flow. A very small amount of stem travel creates a very large percentage of flow in the case of a quick opening valve. In contrast, the linear valve presents a nearly linear relationship between flow and travel. The equal percentage valve, which is most commonly used, is very effective in controlling low flows by requiring a greater amount of stem travel for an increase in flow rate. This produces a better turn-down ratio for better flow control. Equal percentage and linear valves will generally meet the needs of most applications. Putting all three of these together on the same graph gives a better contrast between the different characteristics. While discussing terminology, another very important aspect of valve selection is valve capacity, or the capacity index of a given valve. The accepted acronym for capacity index is CV. The capacity index is a reference to the flow through a valve in gallons per minute, or GPM, at a 1 psig pressure drop. Pressure drop is measured as the difference between the upstream, or inlet pressure, and the downstream, or outlet pressure of a valve. As the pressure increases on the upstream side versus the downstream side, the pressure drop increases, and the rate of flow increases through the valve. The capacity index provides a reference point at a 1 psig pressure drop, which can then be translated into the volume of flow at any given pressure drop that is greater than 1 psig. Different actuator sizes are available for use with various valve bodies, provide both the necessary action and the ability to close off against system pressure. The larger the actuator size, the greater the pressure drop or pressure differential that the actuator can overcome within the valve body. The size of an actuator is referred to as the diaphragm area and is stated in square inches. Robert Shaw valve actuators come in 4 sizes: 3.5 square inch, 10 square inch, 30 square inch, or 80 square inch of surface area. The size of the actuator provides the ability to close the valve against system pressure or to open it within the acceptable limits of the valve ratings. The action of the actuator is referred to as air to close or direct acting and air to open or reverse acting. The combination of an actuator and valve body is affected by valve body construction. In some situations, it is possible to reverse the action of a valve by switching either of the components. The 30 square inch version of the Robert Shaw actuator is available in both a direct and a reverse acting model. This is determined by whether air pressure increased to the actuator moves the stem away from or towards the valve body. The actuator shown on the right is a reverse acting actuator. The air pressure will pull the stem upwards and away from the valve body. It is used with a direct acting or normally open valve body to create a normally closed valve. The 10, 30, and 80 square inch actuators will support the addition of a positive positioner. This positive positioner provides the same effects as the damper actuator previously discussed, the ability to positively position the valve stem in relation to a given signal. This positioner is a different style and has one more adjustment than the positioner for the damper actuator. The valve positioner has a span adjustment, which is a method of widening or narrowing the amount of control signal required to stroke the valve from fully open to fully closed. Here is a positioner attached to the body of the actuator and the feedback spring. The feedback arm is attached to the valve stem. This spring is sized to a specific length of stroke of the valve. Here are positive positioners attached to the 30 square inch actuators, both direct and reverse acting. Note the difference in the mounting styles between the two actuators. Since the reverse acting actuator is traveling in a different direction, the positioner is mounted upside down. The positioner on a normally closed valve does not provide additional force to close the valve, only to open it. This situation is reversed with a normally open or direct acting valve application. In that case, extra pressure applied by the positioner provides additional closing force to overcome pressure drop in the system. In the reverse acting or normally closed mode, the valve spring in the actuator must provide the close-off force. Another area of terminology that must be defined is that of the actuator spring range. This refers to the input pressure change necessary to start the stroke and move the valve stem to its fully stroked position. Some of the common spring ranges utilized are 2 to 6 psig, 4 to 8 psig, 8 to 13 psig, 3 to 12 psig. These ranges are utilized for specific applications depending upon whether a valve is normally open or normally closed, and whether it is a heating or cooling application. The input signal to an actuator, be it damper actuator or valve actuator, is derived from a controller branch line signal, which varies the pressure between 3 and 15 psig. The spring ranges mentioned above fall within the controller output range. and allow the sequencing of devices as required to create the proper control sequence for a given application. This drawing demonstrates valve sequencing. Note the two valves in the drawing: a normally open hot water valve and normally closed cold water valve. Both valve actuators are controlled by a direct acting thermostat. The normally closed cooling valve has an 8 to 13 pound spring range to hold the valve closed when the signal air pressure is below 8 psig. As long as the signal air pressure or the branch line air pressure from the thermostat is between 6 and 8 psig, both the valves will be closed. When the thermostat senses a rise in space temperature, the branch pressure will increase. As it increases, the cooling valve will modulate open starting at 8 and continue opening to full open at 13 psig. When the thermostat senses a drop in space temperature, the branch pressure will decrease. As it decreases below 6 psig, the heating valve begins to open and will continue to open as long as the branch pressure continues to drop. At 2 psig, the valve will be fully open. You've just seen how our carefully designed full line of control devices can efficiently control the comfort demands of modern commercial and institutional applications. We take great pride in developing and maintaining quality in our products. By now, you can see the value of using our line of cost-effective controls that are easy to install and maintain. This concludes the video material for Section 2, Control Devices. Take this opportunity to stop the tape and answer the questions on this section in your study guide. You may want to review some or all of the material in the Control Devices section before proceeding on to the next section. For more information about the devices discussed here, or other tapes covering Robert Shaw control devices for use over a wide range of applications, contact your local Robert Shaw Uniline wholesaler, or write to us here at Robert Shaw Controls Company, Uniline Division, Post Office Box 2000, Corona, California, 91718, 2000.